In this section, we will be discussing non-destructive testing. Non-destructive testing is the use of non-invasive techniques to determine the integrity of a material, component, or structure, or to quantitatively measure some characteristic of an object, for example, to inspect or measure without doing harm to the part. In this slide, you will see some of the more commonly used methods of non-destructive testing. In this section, we will be discussing visual, X-ray, magnetic measurements, ultrasonic, eddy current, liquid penetrant, and magnetic particle testing. What are some of the uses of NDE methods? Flaw detection and evaluation, leak detection, location determination, dimensional measurements, structure and microstructure characterization, estimation of mechanical and physical properties, stress strain and dynamic response measurements, and material sorting and chemical composition determination. When are NDE methods used? There are NDE applications at most any stage in the production or life cycle of a component. NDE is used to assist in product development, to screen or sort incoming parts, materials, to monitor, improve, or control manufacturing processes, to verify proper processing such as heat treating, to verify proper assembly, and to inspect for in-service damage. 6 most common NDE methods. The 6 most common NDE methods used in the industry are visual, liquid penetrant, magnetic particle, ultrasonic, eddy current, and X-ray. Visual inspection is the most basic and common inspection method used. Tools that are used in the visual inspection method are fiberscopes, borescopes, magnifying glasses, and mirrors. Here you see this gentleman on the right using a portable video inspection unit. It zooms the image to allow the inspection of large tanks and vessels, railroad tank cars, and sewer lines. In the lower left-hand corner, you see an item called a robotic crawler. Robotic crawlers permit observation in hazardous or tight areas such as air ducts, reactors, and pipelines. Liquid penetrant inspection. The steps used to perform liquid penetrant inspection are as follows. A liquid with a high surface wetting characteristic is applied to the surface of a part, and the penetrant is allowed time to seep into surface defects. 2. The excess liquid is removed from the surface of the part. 3. A developer is applied to pull the trapped penetrant out of the defect and spread the defect on the surface where it can be seen. 4. Visual inspection is the final step in the process. The penetrant used is often loaded with a fluorescent dye, and the inspection is done under UV light to increase test sensitivity. Magnetic particle inspection. With magnetic particle inspection, the part is magnetized. Finely milled iron particles coated with a dye pigment are then applied to the specimen. These particles are attracted to magnetic flux leakage fields and will cluster to form an indication directly over the discontinuity. This indication can be visually detected under proper lighting conditions. Magnetic particle crack indications. In this slide, you will see a crack-like indication in the throat of a crane hook on the left. The same indication can be seen in the surface of the sprocket on the right. The radiation used in radiography testing is a higher energy, shorter wavelength version of the electromagnetic waves that we see as visible light. Note that radiation can come from an X-ray generator or a radioactive source. With film radiography, the part is placed between the radiation source and a piece of film. The part will stop some of the radiation. Thicker and more dense areas will stop more of the radiation. The film darkness, which is density, will vary with the amount of radiation reaching the film through the test object. Lighter area of the film indicates less exposure. darker area of the film indicates more exposure. Radiographic images. While looking at this slide, you can see how nicely the radiographic image represents the actual part. Eddy current testing. Here we see an eddy current field being induced on the surface of a part. The part is a conductive material. Above the heart, held perpendicularly, is an eddy current probe. As the probe approaches the conductive part, a magnetic field is created in the probe's coil. This field produces an eddy current magnetic field, which in turn creates an eddy current field on the surface of the part. Eddy current testing is particularly well suited for detecting surface cracks, but can also be used to make electrical conductivity and coating thickness measurements. Here a small surface probe is scanned over the part in an attempt to detect a crack. Ultrasonic inspection pulse echo technique. As high-frequency sound waves are introduced into a material, the sound waves are reflected back from surface or flaws. On the left is an oscilloscope screen. This screen shows reflected energy that is displayed versus time. This display enables an inspector to visualize a cross-section of the specimen showing the depth of the feature that reflected the sound. Ultrasonic imaging. Today's technology in ultrasonic imaging allows high-resolution images that can be produced by plotting signal strength or time of flight using a computer-controlled scanning system. On the left is an image of a quarter. This is a grayscale image produced using the sound reflected from the front surface of the coin. On the right is a grayscale image produced using the sound reflected from the back surface of the coin, which was inspected from the head side.